Okay, then I started with this slide because I want to say thank you to Maria Laura. This is a seminar part of the alumni network. As you can see, there is presence from people from all over the world, and thank you, Maria Laura, for keeping up this important work for the institute and for everyone. I think all of us as alumni that study at IHE are very interested in keeping always up to date with different things. Just one fast question. I just want to confirm that you are seeing my slides. Abraham or Jose? Yes, everything's there. Okay. Now, what I have prepared for today is precisely this discussion about what is artificial intelligence, how artificial intelligence is making a change in water resources. And I'm seeing from the perspective of hydroinformatics. And hydroinformatics at IHE has been bringing this together in different ways. I have to acknowledge a lot of this work. Professor Dimitris Solomatin have been here already for some years at IHE, and he has been always pushing new technologies, implementing new areas, always something that can be applied and can be new is studied, it's implemented, it's tested, and therefore what you're going to see here goes like in that framework of ideas that have been developed at IHE. So where to start in all these things? This presentation is artificial intelligence, and it could be interpreted as complex as if you go to the Stanford Encyclopedia of Philosophy online, you will see that is the field devoted to building artificial animals, or at least artificial creatures that in the suitable context appear to be like an animal. And for many artificial persons, at least artificial creatures that is suitable context. So as you can see, it's very, very cumbersome definitions that, well, we really don't know how to understand that. But if you go into a simple, not so technical description, or well, maybe approved one, Wikipedia is mainly used for this type of finding information and descriptions. And Wikipedia says that is intelligence demonstrated by machines. Then now it's more up to something that we can understand, a machine that is an intelligence. And unlike the natural intelligence is displayed by animals and humans, this is different. It's leading artificial intelligence nowadays talk about intelligent agents, and these agents are devices that perceive its environment and take actions that maximize its chance of successfully achieving its goals. And this can be, if you look at that sentence, it can be just a simple sensor on the wall where you just pass and the light turns on. You pass and the doors open. You enter into a room and the temperature regulates. You enter to a room and the light regulates according to the day, such that you have a friendly environment. So these many small things can be interpreted as AI type of things, and this goes even with the concept of some people in electronics called domotic that make intelligent houses. You clap your hands and the lights turn on, or you say a voice and talk to some device and device opens the door, closes the doors, select alarms, and so on. That's called intelligent houses. So indeed, this definition fits kind of this type of things. Another part of this definition, it says the colloquial term artificial intelligence is often used to describe machines or computers that mimic cognitive functions that humans associate with human mind. And that's another point of view that in the same context, computers are these machines, right? Kind of develop, analyze, and provide some responses in the context of what you are telling them. So artificial intelligence, so far, yeah, it's kind of having some sort of machine that helps to respond in a certain way, understanding what is around it. Okay. Now, where this came from, we can say that the computers came in, from the first thoughts and the mind paper of 1950 from Alan Turing. He argues the question: can a machine think? And 6 years after this question came from Alan Turing in this paper, the concept of the term in Dortmund Conference in 1956, artificial intelligence born. That was the first time many researchers started to talk about artificial intelligence. So from that perspective, we have computers, where it started the concept, then programming on top of the computers, then came internet, it was a change in paradigm, and it started to still have a lot of things ongoing. And the last part is artificial intelligence on top of all these things. So what I'm going to present in this following 25 minutes will cover the development, and at the end I will show 4 examples of artificial intelligence now from the most modern concept point of view. But I will show you different paradigms that have been growing, and you are still probably, people working in water resources are working with some of these paradigms in day-to-day life. So the first thing was the computer, the device, and that device, the computer, every computer has some memory, and you will see about the RAM memory when you're buying a laptop, the memory long term, that your hard drive, and you want to move it from one side to the other to your USB. You have, every computer have a central processing unit, so it will process all your information, and every computer have a ALU, which is an arithmetic logic unit, which will process the mathematical component of that. And then you have periphericals that are the ones that allow you to interact with the machine. So kind of the computer already is kind of mimicking this concept of what is needed to be able to understand some artificial way to reproduce things. After we got the computer, then we started to program on top of it, so solve many tasks. How can we make computer do more and more and more things? And this was a boom from all type of areas of science. Then the main goal on this, as you see here in the second part, is automate or program activities. How can I reproduce a very complex problem that I solve in one place, create a program, and use it to solve another and another and another? The main principles of this automation in programming has only two components. The first one is just have a logical decision. If you have some condition, then do something. That's the basic principle of programming. And the second basic principle of solving are loops. So how can I do something many times, iterated? So for a condition, do something until something happens. So you have these two components that allow you to do almost everything in programming. And that's, I would say, is the main, let's say, challenge to how to use these two components to build and build and build and build much more complex automation with a computer. But that was the beginning, and the beginning growth into programming in water resources. And this was, I would say, hydroinformatics. That programming and that idea of being able to use these tools came with the numerical methods to solve physical equations. And we had, in those days, hydroinformatics. Michael Labot, IHE Delft in the Netherlands, started to think about how can we build models that can represent fluid dynamics from the basic equations. So they started to move from what was before a conceptual model, a model, physical model, into much more complex representations where we solve the fluid equations. We can evaluate cross sections in a river, see where they are going to inundate it. We can build hydrological models that flow, that can show the flow that will happen in certain moment, inundation areas, water depth, and so on. So that's kind of an example on this part of programming. But it didn't stop there. And when you finish that concept on programming, you move into internet and the cloud. And how internet and the cloud started? Well, you had these machines, we had these models, you just saw them in water resources, at least this example is in water resources, is how they can communicate How can one office that has one information in one place and another has another, how the computers can communicate, and then it moved, we need to communicate faster, so they started to create the networks between computers. But then we need to share information, and then the networks start to grow and grow, capacity, distance, and so on, and reach a level where the communication and information was not constrained, was open. So everyone could move and start to add the information, and this ended in the new social world of digital citizens. Everyone has its profile, everyone has its place where they are sharing what they are happening. There are different types of spaces where you can contribute and you can say what you are thinking, what you are doing. So that created a kind of an unexpected space in this technological development. But as well, there was a competition in one side from all the internet. If you have a large technology that covers all the world, you have a lot of information and want to search along it. How to solve this problem of searching through hundreds of thousands of data. And that was the different internet searchers. There used to be Digital, Alta Vista, there was Yahoo, there was MSN, Hotmail. Still, there are many search engines. But Google took the lead. It seems that it was able to respond to what the people wanted. If you want to know about something, then the most accurate one was Google, and then let's say the company became rich. It would be largest in the world in that moment, only because of the search engine. But to complete the story of what these have provided us, it end up in now this search engine became like a kind of artificial intelligent space where you can nowadays ask what's the weather in any country in Latin America, what is the currency conversion right now, what is happening in Australia. So you right now you can even say, how can I cook something? Where can I find a place to replace my thing? So as you can see, this starts to become an kind of intelligent responses to everything that you want, and it's only based on searching through databases, only looking what is there. It's nothing really intelligent behind, but it's answering all the questions that you have. That paradigm in water resources end up in what we have right now on water-related data, information about the weather, sensors in real time that we can have right now at different devices, information about extreme events. This is also an important thing because in the past, something could be happening in Africa, in America, in Latin America, or whatever, and no one knew about it or was not so well informed. But now everything is connected. So it would appear that now you can understand what is happening worldwide. Before it was not possible. And the concept of remote modeling in water resources, this was something very interesting. In the year 2002, they started a program called Hydroeurope. And this, I mentioned this because it's the concept where I started to see for first time remote modeling. How can people access models, complex systems through internet? And Hydroeurope in 2003, in fact, this is my badge on the Master of Science in IHE. I am there somewhere with some glasses. And also Professor Joanna Popescu, which was the leader on this program through Europe, and there were 4 or 5 countries. And what they wanted to do with this program is that we all in different countries were accessing the same model, but each one working in some characteristics and problem. And we had to build a project out of all these very complex information systems. And at the end, we went all into France and Nice, and we met the people. We met we went along the region, understand the things that were happening. But before that, we were 3 months working online with remote systems. So this was an interesting change in paradigm. Everyone started to think about how to do models and to be able to share them. Now, reaching the area of more advanced things in water resources, we can say that this end up in, now we have more information. There is a boom of how to deal with extreme events. You can see that due to the fact that the news about the events are happening everywhere, we are not more aware. So now we want to deal with extremes. We want to see how the other people are dealing with extremes. We want to be more informed and knowledgeable in the areas of risk, how much risk right now I'm having. Right now we are more prone for experience like which type of models are they using? What type of infrastructure have they implemented? What sustainable development interventions can I do? All this information is there. Now, the last thing that you can see in this boom of the internet is that now you have social media in water. If some expert in water wants to find a job, that's water jobs. If there are many groups about risk in extremes, in floods, in droughts, in water management, diplomacy, and so on. There are government awareness organizations, social media, even Facebook for cities, for regions, for awareness of extreme events, and so on. So this is very interesting that it came into that. But now that I moved the last, I think I counted myself 10 minutes to reach here. I don't know if it took 10 or less or more, but this is artificial intelligence now. And what you are seeing in these slides is the concept on different specialized websites about how the artificial intelligence developed, which basically is what I said in these last 5-10 minutes. Is okay, the concept started, but it was a little bit vague. Everyone was thinking about what can be and what is, and there was always fears of what can be reached. The 1980s and 2010, there was machine learning moving and starting, and from 2010 there was a shift in paradigm again on a competition, an international competition on image and pattern recognitions, where an algorithm that used deep learning made a breakthrough. It managed to improve the performance of the classifier, or to identify things with impressive accuracy and relatively very fast. And nowadays, any one of you can install in 5 minutes this network of 23 layers, and you can identify many objects. There is a test where you put the camera and you put your cup, or your coffee cup, and it will tell you that's a coffee cup. It is really simple. That's I encourage you to explore these type of things. It's really simple and so on. But okay. What is the context of artificial intelligence and deep learning and machine learning? I would say the machine learning in general, it's more wider, and that's why here I will talk of most of the things about machine learning. It's the ability to learn without being explicitly programmed. And that sentence makes a very important shift in paradigm. So nowadays, there are many people saying you don't need to learn how to program. Now you just put a machine learning that will program, in between brackets, program the thing for you. What's the meaning? You have inputs and outputs, and in the past you had to learn what were all the processes, and you had to program all the processes to be able, with one input, obtain one output. Now not anymore. Now you start to think about, oh hey, I have this data from the input and I want to obtain these outputs. Every time that I have this combination, I need to have this type of responses. And then if you build a table that allow you to know what is happening inside from the action and what is the consequence, you can build a neural network without having to program thousands of lines of code. And that's one of the things that I want to show you here, how it works. So in this concept, artificial intelligence is building from knowledge from mathematical equations. It's a framework. Let's say now we are here talking more in detail on machine learning, and it's built from different areas of science. So terminology sometimes in different papers starts to be cumbersome. So experts in finance talk about artificial intelligence and machine learning precisely in their own terms, and they develop their own algorithms. People that are working in image recognition, another one, people that are working in databases and big, large databases talking in other contexts. So that's why having all these areas of development requires some time to be understood and know what is the best to do. It's not magic. You cannot just select one thing and will solve your problem. You need to really go a bit deep into it. I don't know. Somehow I lost the presentation. I don't know if.
Hello.
You can see it there, Abraham.
Can you hear me?
Yes, yeah. I can hear you.
Would you like me to bring your presentation back?
Yes, please. Sorry, yeah. Somehow I pressed to change.
No, not this.
Yeah, thank you. But you say it's not.
Yep. Do you see it now?
Yeah, that's it. Yes, I see it. Thank you. Okay, now continue with the concept of machine learning, and now I want to bring more ideas and bring that now down to earth, so you understand what is machine learning, and this will open a bit the scope for what Theo and Jose will present in a few minutes. So what is machine learning? So the machine learning is described as the use and development of computer systems that are able to learn and adapt without following instructions. Okay, and then here you have inputs and outputs on the right. You have a real system, and what you want to represent is that when something happens in the system, you have some output that you are measuring and you're observing, and then you want your machine learning to learn from that experience and receive the same input, know what is the output, and he will produce an output, and you need to differentiate if the predicted output should be equal to your observed output. And this is trying to learning is minimized the difference between both. So how can you change the parameters inside the machine learning data-driven model to make the best prediction on what would happen in real life? And this slide is from the lecture from Dimitri Solomatin in IHE in 2009, and where most of this concept of machine learning has been explained as data-driven models. So you will find a lot of literature publications where machine learning has been described in this area of science as data-driven models. Oops, again. Somehow, if I press space, it jumps here. Sorry, Abraham. I will try not to press space. Okay, now, to understand a bit more these systems and how they became how they work, and why they start to become complex once in a while when you start to grow the problem, is this thing like a transition from one neuron. What is one neuron in these concepts of machine learning? And I'm giving the example of one of the most well-known algorithms, which is the MLP, multi-layer perceptron network. So everyone that thinks about machine learning identifies it with neural networks, although it's not like that. There are many types of networks, and there are many types of algorithms that are part of machine learning that are not neural networks. But in this case, I wanted to mention this as the core because, well, some of the things that are going to present Jose and Theo are in this area of work. So one neuron is simply like what you're seeing on the screen. It's like a kind of linear regression. You have x1, x2, x3 multiplied by a weight 1, weight 2, weight 3. And if that combination of values of your inputs multiplied by a W is a number that you need to fit, such that your value of A will tell you that is 1 if it's one class, and 0 is if it's then the other class. They call this activation. So it activates and says, for example, it's above the threshold, it's going to be a flood. It's below the threshold, then it's not a flood. In normal machine learning, or when you are looking in other areas of science, it says, oh, that's a dog, not a dog. It's a cat, not a cat. You know, it's black and white. And this was more or less the most simple way to see these activation functions. The next level is to see it in this two-dimensional. So this regression, in fact, is a line. And what you are trying to find is the slope and the place where the line should go, such that you classify all your points in according to what they are. So you already know that the blue points on the right are one class and the crosses are another. So you need to find the slope of this red line. That slope is this W, and the bias parameter, of course, to displace it. And if you find that exactly divide both, then you have a classifier. Everything above the line is a cross, below the line is a dot. That's the first concept of one neuron, which is this one. But what if you combine that with another, with another, with another, with another, and with another, and finally with another, and you have what is called a multi-layer. So each one of these rows or these columns each one of these rows is one layer, and that's what they call this multi-layer. And this was one of the beginnings of neural networks, and they say that this is a universal approximator. The challenge here is that you have so many nodes, and every one of these lines that you see, there is a weight, and to be able to learn, and the learning is identifying those weights. Well, how can I find the weights that will perform the task of classifying or being able to let me know that certain combination of inputs will have some result? And as you can see, that's the challenge, learning. And learning is an optimization problem. How can I optimize the weights such that they will produce what I want? So where these machine learnings are applied, so you will find experts in finance time series that works with things like this, or even in voice recognition. But in water resources, we use it to forecast or to simulate rainfall runoff. Options, pattern recognition, you can find it like this in other areas of science. In water resources, we try to look at remote sensing images to try to identify patterns of floods or patterns of crops or whatever. In other science, large colliding hadron physics. In water resources, we have big data in atmospheric science. Every second, in every place on the Earth, every minute, every hour, every model simulating a scenario of climate change, you have big data there. In text mining, we have in general in internet, Google systems and so on. In water resources, well, we are just right now starting to understand how can we convert this qualitative data into quantitative data. Now, again, going deeper, where is this AI in water resources? How can, and you can find many applications nowadays that use machine learning for simulation of events, from forecasting rain or discharge for early warning systems, and even building surrogate models that replace operational systems. So like real-time control situations where you want them to reproduce or represent something that you want to achieve certain performance. So this first paradigm in water resources contemplates only time series, and there is most of the time no spatial information. The second one is the image classification in remote sensing. So there are many algorithms, and you go to Google Earth Engine and you will find classification problems in remote sensing images, mainly about land use, flood classification, and so on. So how can we learn that some pixel in a survey was identified as a certain type of crop or certain type of grass or whatever, Then you go into the image and you look at the place where you did the survey, and then you make your remote sensing image to learn this result in every pixel, and then you say, okay, now that I know that combination of bands in my remote sensing image give this value of colors, that colors in fact is a class which is a land use. Then I will use it for the whole image, and then you reproduce what is happening. So mainly these type of problems are spatial or georeferent information. As you see, they do not work in time. It's only one layer, or it's a spatial representation, and you want to identify what is happening everywhere. And if a new image comes, you also would like to try to explore the same use of things, but it's not explicitly in time. The third area of application of artificial intelligence is in decision making. And I would say that the last 10 years there have been approach of using text mining. And recently, I would say in the last 2 or 3 years, there are people who are working with natural language processing that has advanced quite a lot. To take information from social, qualitative information. This information is highly abstract and dynamic. It's changing every day. The news, the people tweeting, Instagram, and so on. So all this information, how can you take this information to obtain, okay, you look at this information and obtain something that is useful for either for your models or for taking a decision. And number 4 of the ones that I know I'm aware of all these, some of these applications, is the spatiotemporal models. So let's say agent models, cellular automata models, pattern tracking. So how spatiotemporal information of dynamic nature can be seen and can be used for replicating what is happening in real life. So let's see the context. These are the 4 examples, which with these 4 examples I will finish my presentation. I hope not taking too much time because we started late. The first one is flow forecasting. I mentioned it before. If someone wants to make a flow forecasting with physics, you could go with a very complex physically based model. Most of the time, flow forecasting systems work with conceptual simplified representations, even with the statistical representations. And this is one conceptual model, and although it's one of the simplest models, it has many parameters. What has been with the applications of neural networks is to try to say, okay, what are the inputs and outputs of that situation? So, or either you go to the conceptual model and you program every equation and say, if this is happening, then do this, and if there is a saturation of the flow, then do that, and if there is a level of the groundwater, then put some percolation and change it, and put some runoff and so on. So you can put all these type of complex equations, or 2, say, okay, let's build a machine learning model, in this case a neural network model. What are the previous time steps, which are in fact the inputs of the normal conceptual model? What is the PT, precipitation in time -1, -2, -3? So what's the lag precipitation? What is your lag discharge? And then what is the output of that? What is the discharge at the next time step? Or what is the discharge at the following forecast horizon? And this is how the network learns the real system, and then when you use it in real in operation, it will reproduce. This limitations is that it is fixed time steps. So whatever you give him is what he's learning. And most of the time you read only the measurement from your device. That makes it well, there is no knowledge representation, and it's fixed on your delta t. In a conceptual model or a physical based model, you are representing the physics, so you can play with time. In this type of models, not. A second example is the optimal reservoir operation, and this is in Dominican Republic. The MSc research of Carlos Tami from Escuela Colombiana de Ingeniería. He just finished, in fact, this week, and was very interesting case. So that's why I am bringing it here. This is in the river Juna and the Reservoir Atillo, which is one of the most important in this river basin, and it has there have been many floods in this region. The reservoir is meant for producing energy. It also helps on the irrigation district, and also has been discussed. Oh, sorry, again, space. Abraham, yes, sorry, can you help? I cannot hear you. Somehow it's mute.
How about now?
Yes, now I can hear you. Yes.
Okay. I just wanted to ask you to please start winding up. We are running a bit behind time.
Yeah, it's only 2 slides more. Yeah.
Okay. Thank you.
Good. Yeah, sorry for indeed I was thinking it is 30 minutes, but probably. Yes, thank you, Abraham. Okay, so this is the case study of the Juna River, and let's imagine that, in fact, this is not good, but okay, let's go backwards. Let's imagine that you want, we have the last 12 years of operation of this reservoir, and there have been many floods, and there have been many situations where there was not enough water for the crops in the region, and it was in fact operated trying to satisfy everyone, but mainly energy production. And that, if we look in detail, why we don't try to learn from what they have, and this is a relatively recent concept. You learn on the past, you build a model that represents what is happening, but after you learn that model, then you say, okay, now I have a representation, and I want to, in the future, to solve the challenges of the system. I need an optimal energy production, and I need a reduction in the terms of flood situation, and I need enough water for my crops. So here we build a neural network model where the 3 objectives. This was built to reproduce what was there happening, to reproduce what you can see in the blue line. The rainfall is on the upper part. That's an average rain of the system, and the lower line is the green. That is the energy production, and the artificial intelligence. There were many models built, and finally we got one that managed to reduce the floods. And you see the blue and the red line on the middle graph, and all the events. Yeah, maybe 80% of the events were solved by making an intelligent machine learning to take the decisions. And this was built on past experience, and then optimizing what will be the maximum reduction that you can have in flood with the maximum production of energy, with the maximum satisfaction of agricultural irrigation. Okay, and then this is third example. As I said, it's only 4 examples, so Abraham, I'm almost going to finish, sorry. Just mention the PhD studies of Vitaly Diaz. He's the one that working in these special droughts. This is a case study in Eastern India. This region is very famous for the production of rice, and there is a situation where if you have a drought in this region, well, you will impact in your crop yield. But the region is so big that to be able to make a survey and to analyze the impact, it will take you like 2-3 months to be able to understand how much was the impact. So we look at past situations and how much the crop yield was impacted, and we made it learn. And by looking at the spatio-temporal variations of the droughts, there is an animation here that I see is not working. But okay, what is supposed to happen is that these areas starts to change. By learning the changes in the areas, we could determine how much drought, how much crop yield will be affected. Now, this work was extended, and what you can see here is the whole India, and what we are finding the variations in space and time of each one of the events along a certain number of years, and I think this was 15 years, and then we look at how the patterns, and we made a tracking of all the large events. In the lower part, you can see the vectors that show how are the droughts appearing. And via doing this, you can identify when a drought is going to happen, how it's going to happen, what is the synchronicity of the drought. So this is very, very interesting, and this is all looking at the pattern tracking motions. And the last one is the example from the new social media. This is also very, very new. It was in a competition of artificial intelligence in Colombia with 22 universities. And the concept is how to bring the qualitative information from the network. And what was proposed by Santiago Duarte, PhD student from Colombia, was to create a system that was scrapping. We navigated through the internet, started to extract information from all the newspapers, more than 4,090 news articles. And after extracting, he processes with a natural processing language, extracting intelligently the information such that you can have an index that will tell you that is good or bad. And he created this app that you can see in the address http Santiago Duarte 09 users earth engine.app. And what is going to show you is something like this. This is one of the 6 apps that you will see there. And what it will show you is the feelings of the people and how this has an index of the health of the rivers, how they are feeling that the river is in a bad condition, a good condition. Since this analysis is done historically, it was mapped with decisions made by people in the regions, and we were able to see what wrong decisions led to decay in the information that was from the news, from the people, and from the social media. As well, when there was success in a decision, we also felt the feeling of the people around the system. And that's it. That's my presentation. So that's what you think will be the next AI application in water resources. What this is just to spark ideas, and I hope the ones of Theo and Jose can complement, and they for sure will go deeper in many things.